Hello students, today we are in last lecture we have done the example based on them. Today we are going to see one more example based on this dam, and we will complete this topic of the dam. So let's start. So here for this trapezoidal masonry dam as shown in this figure, we have to plot the stress distribution at the base. The density of the masonry dam that is given to us as a 20 kilonewton per meter cube. So let's see the figure, what is given to us in the figure. Here in the figure, the top width, that is A, that is given to us as a 1 meter. Okay. Second, the base width B, that is given to us as a 3 meter. Okay. Now third, the total height of dam is given to us, so the water is retained. So in this dam, what happened, the water is retained up to this height only. So up to this height, from this base, the water is retained. So in this portion there is a water. Okay. And this portion, so this portion is pre-bore. So the height of this water portion, that is given to us as 4 meter, and this 1 meter, that is pre-bore. So total height we can say that is 4 plus 1, 5 meter. So the total height of dam from this up to this bottom, that is so the total height, that is 5 meter. So let's write it in this. So the total height, that is 5 meter. Okay. And this 1 meter portion, that is known as a free board. Okay. So from the figure, what data we will know, that will write over here. The top width that is given to us A as 1 meter. So the top width A, that is given to us as 1 meter. The bottom width that is given to us as a 3 meter. So here we will write bottom width B as a 3 meter. The height of water HW, that is given to us as a 4 meter. So HW, that is given to us as a 4 meter, and total height, that is H, that is we know it is 5 meter. Okay. And density of material rho D, dam material, that is given to us as a 20 kilonewton per meter cube. Here the density of water, that is not given, so we can take it as a 9.81 kilonewton per meter cube, or we can say we can take it as a 10 kilonewton per meter cube also. So here it is taken as a 10 kilonewton per meter cube. Okay. So these are the data that given to us. Okay. Based on that, first step is what, we have to plot this stress distribution diagram. Okay. So the first step, what we have to do, we have to compute the forces that acting over this dam. So the first force that acting over this dam section, that is the water pressure distribution, the first force that act over this dam, that is water pressure. So this triangular portion is what? Water pressure distribution diagram. Okay, so its intensity at the base, that is equal to what? Gamma into HW, gamma that we know and HW that we know. So based on that we can compute the total pressure PW, that is area of that triangle, that is 1 by 2 into base, that is gamma into HW, into height, that is HW. Okay, 1 by 2. So gamma W that we have taken 10 into HW, that is given to us 4 meter, and again it is HW, that is 4. Okay, so by this calculation we can find out it will become 10 into 4 square divided by 2, 10 into 4 square divided by 2, and we can easily compute this value of this PW, that is coming out as a 80 kilo Newton. Okay, now we have to compute this second major force, that now we have to compute the second major force that is acting over this dam, and that is the weight, self weight of the dam. So self weight of the dam will be equal to what? So that will be equal to nothing but area multiplied by density. So the area will be equal to top width plus bottom width divided by 2 into height. The top width is 1, bottom width is 3 meter, divided by 2 into height, we can say that is given to us 5 meter. Okay, into density of material, that is given to us as a 20. So here it is same as this. So by computing this we can get as a 200 kilo Newton. So we have done the calculations for the two major force that acting over the dam, that is the water pressure, and second one, that is the self weight of the dam. So now based on these two we have to compute this Z. So to compute this Z value we need a x bar only. So x bar, that is the CG, the equation of CG for the trapezoidal section that we know. By putting the data in this we can easily find out the x bar. By putting the x bar in the equation of Z we can find out the Z value as a 0.72. By knowing the Z value we have to compute now the eccentricity, that will be equal to Z by 2 minus, that will be equal to Z minus B by 2, Z minus B by 2, Z coming as a 0.72, B that is come with us, that is 3 by 2, so that will be becomes a 1.5. So your E will becomes a negative 0.78. Okay, so here the most important thing that you have to keep in your mind, your E will becomes negative. So here what it want to say, that need to be understood. So let's make it highlight, it is important. Here the eccentricity is negative, hence maximum stress will be at hill and minimum stress will be at toy. It is, if the eccentricity is negative, then the stress position will be a change. So here the maximum stress will be at hill and the minimum stress will be at the D. To calculate this string, but again here this is the note point that you have to keep. To compute this maximum and minimum stress, you have to use the value of eccentricity without considering the sign. So in the equation we have to put E as only 0.78, not the minus 0.78. That thing you have to keep in your mind. We have to for the computation we have to use the eccentricity as only 0.78. Okay guys, understood? Now next, so now we have to use this equation of sigma max. So the sigma max equation that we know, that is W by B into 1 plus 6E by B. So we have computed this W as a 200 kilonewton. Here it is W. So here we have computed this W as 200 kilonewton. Okay, so we have to put W as 200 kilonewton. B, that is the base width, that is base width B, that is 3 meter over here. So we have to put the B as a 3 meter over here. 1 plus 6E by B. So E, that is the eccentricity. We have computed the eccentricity E as here 0.78, but we have to minus 0.78, but we have to put only over here the plus 0.78 only without considering the sign. B, that already we have seen, that is 3 meter. So we have to put this data in this equation and do the computation. By computing, we will get sigma max as so we will get the sigma max as a 170.67. So we'll get the sigma maximum as this. Okay, so next we have to compute this sigma minimum. So sigma minimum will be equal to what? W by B 1 minus 6E by B. So W, that we know 200, B, that we know 3, 1 minus 6 into E, that 0.78, and by B, that is 3 meter. By putting this, we will get the tensile stress as negative. Okay, so now we have to draw this distribution diagram. So how we will draw? Let's say, so here in this portion there is a waterfront site. So the water is present in this portion. And the water is present over this portion. So dam body. So it is dam body. It's a reservoir. It's a dam. Okay, so here on reservoir side it is hill, and on this it is a top. So it is hill, it is top. So here the maximum pressure sigma max is acting at hillside, and the minimum pressure is acting at this top, which is the negative one. So here we have seen the diagram will be a look like this. We'll draw it big one. So here in this case the diagram will be look like this. here the pressure will be the negative sigma minimum, and here the pressure will be the positive, that is sigma maximum. So it is positive, it is negative. So likewise this we can plot gas distribution diagram for the dam. So in this example what we have seen, so simply the figure will be given to us for the dam, and the data we have to get from this figure, and we have to draw the stress distribution diagram. So for the stress distribution diagram, first we have to compute the what are the forces that acting over this dam, and based on these forces we have to compute the sigma maximum and the sigma minimum, and we have to draw the distribution diagram like this. Here the thing that you have to understood in this, that is where is hill and where is tau, where is sigma max and where is sigma minimum. This thing you have to kept in your mind. If you kept this thing you can in your mind, then you can easily solve the example like this. So here what we have completed in this module, the chapter that is direct and bending stress. In this, first what we have seen the theoretical portions, that is equations for combined stress, so what today we have seen, that only we are going to conclude over here. We have seen the dam theory, and the dam example. Next what we are going to do, we are going to solve the example and theory based on retaining wall, and next we'll go for the chimney. Okay, so and then we will end this chapter. Okay guys, so thank you everyone. So here we end this lecture.